No, I'm an idiot.
Well, I wouldn't go that far. And then anytime that a nitrous bacteria eats an ammonia molecule, we're modeling this as it being able to produce a new nitrous bacteria. So it's like a 1-to-1 exchange from ammonia into nitrous ammonia. Okay, so there's a lot of different problems with this. One of them is that this does not take into account that nitrous bacteria have like some sort of lifespan, right? They're supposed to die eventually, everything does. So we need some sort of negative term here. That's easy for us to take care of. But also it doesn't take into account things like, what if nitrous bacteria are sensitive to ammonia, even though they eat it? What if it's in such great concentrations that when they eat it, they die? Like, what if it's poison at high enough concentrations? What if their birth rate as a function of ammonia concentration is like unimodal, right? There's too little where it's not going to reproduce very much, and there's too much where it's just going to die. We would just wrap that under the, or sweep that under the rug for this model, and we're not even going to worry about it. But I'm going to write it down so that I don't forget. Okay. Now, if this was the only thing that I had going in my model, how many of you guys would be comfortable solving it at this point? You can solve. Find solutions.
Find the fixed points, find the.
Yeah, so this is one of the fun parts about differential equations is when I say solve the problem, there's like so many different things to do. First, you gotta find the fixed points, then you gotta check the stability of the fixed points, and then you gotta find all the isoclines, and then determine whether or not there's a bifurcation when the isoclines vary as the parameters vary, and so on and so forth. Woo! So when I look at this, I immediately think to myself, how can I make my life easier? And when I do that, well, first off, we can take Matt's advice and immediately look for equilibria. The equilibria are when the derivatives are, I see people say it, it's 0, right? So if we're going to look at this thing and just find the equilibria, just this simple system, then what we do is we set this equal to 0 and equal to 0, and we kind of look at a plot. But we're going to plot it. What are our two variables that we're plotting? A and X. Because it's just easier. Why worry about time? In this case, if I set this thing equal to 0, what do I get for A? With the BAX over divide by beta AX, and divide by beta X, we get alpha over beta X. Excuse me. And alpha over beta X looks like this. Everybody agree? Now, if this one equals 0, what do you get? What happened? What's different about this compared to this? Huh? What did you say?
Oh.
Well, we set it equal to 0, but what's the difference? What's one major difference that you see between this equation and this equation?
It's constant, the other's not.
So this is constant, or this isn't, I mean, we have two variables here, we have two variables here, we have two variables, two unknowns. But what's special about this term and this term that they have in common? X. So, which happens to be, well, actually, we haven't shown anything about X being 0 yet. All we've solved is that A for the equilibrium is alpha over beta X. But if we solve this thing, we can pull the X off to the side. This is a trick that everybody in here should know. Now, everybody here in the back was like, oh, so X is 0, right? This is why maybe it's not 0, because this term could be 0, right? So the solutions to this term being 0, one of them is x equals 0. Oh, x is 0, I guess. Sorry. Another solution is a equals lambda over beta, which happens to be a constant lambda over beta. So one of these solutions falls on this curve. One of these solutions falls on this constant line. Where's the solution? Right. So this is our equilibrium. Now, one of the interesting things that I find with problems like this is that we didn't just compute the equilibrium, but we plotted a couple of curves. And actually, this diagram has a lot of information in it that we will find very useful. Here's why. Let's say, I'm going to write this again up here so that I can have a little bit more space. Let's say you have an initial condition for this differential equation that starts just above this line here. Which direction is it going? I have an initial condition that starts here. There's going to be a unique trajectory that has to pass through this point. Which direction is that trajectory pointing? Starting at that point. Well, this is a fun problem to think about. We know that we're above A equals lambda over B. So at this point, we know that A has to be greater than lambda over B. Right? So what does that tell us about this term? Let's assume all the parameters are positive, by the way. It's positive. So we know that wherever you start at that point, you have to be moving upward. Okay, right? That's simple. And
So that other way. Dx right.
oh, it's dx dt. You're right. Thank you. See, and this is how you know that people in your talk are actually understanding what you're talking about, is if they correct the mistake that you absolutely intentionally inserted. Okay. What about dA dt? At this point, we're moving up or down. Matt says down, Jared says down. Anybody think up? I don't think up. Well, let's check, right? We know that at this point, we're above this rounded curve. So we have to have alpha greater than alpha, excuse me, A greater than alpha over beta x. You can totally see that I've merged the Greek and English alphabets in my head already, now that I've graduated. So in fact, in this region up here, A is also greater than alpha over beta x, which means A is big, which means this quantity has to be negative, right? So we're moving down. Now, why is this important? This is kind of how we construct phase diagrams for very, very complicated differential equations. We restrict ourselves to 2 different dimensions, and we start drawing arrows. First, we draw where the equations are 0, and then we look at all the different regions that we have to consider, and we look at what the arrows are. In this case, we know that we have to be moving down and to the right in this region. Everybody agree? When I cross this line, actually, in fact, at this line, am I moving up or down? Down. But I'm not moving left or right anymore. Because I'm on the point where the left-right variable is not moving anymore. So I have to pass directly through that line vertically. Then when I'm in this region, well, now it's pretty obvious I must have changed direction. Now, when I hit this nice curve, I have to be moving just horizontally. And then once I'm in this region, the only other option is that now I'm moving up and to the left. And then when I cross this line again, I have to be moving vertically. And then now I'm moving up and to the right. So we can kind of visualize how these trajectories should go without solving a single problem more complicated than algebra. Because now I can draw this, by the way, great album, Polygon Wonderland by King Gizzard. Now that it's recorded, it's in history. So looking at this, we can we can conclude that our trajectories over time kind of look like they might be spiraling into the center. Right? How can we tell if this is a spiral or not? Because I drew this as a stable spiral. It's coming into that equilibrium point, but I could have drawn it the other way. Or just reverse time, I guess. But then you have clockwise-ness, that doesn't quite work. So the question is, how can I tell that this is a spiral and not like meeting with itself in a loop or spiraling away? How can I tell? Teachers aren't allowed to answer the question.
When you check points here.
We can just check a couple of points near the point, but, which is a great phrase, but this is a high dimensional space. We're drawing it as two-dimensional, but remember we're like in fifth dimensional space. And if you want to sample, like let's say that we were smart and we put that equilibrium right in the center of a cube. And then we're like, all right, I'm going to sample each corner of the cube. How many do we get in three-dimensional space? 8. How many do we get in fifth dimensional space? 2 to the 5th is 32. So sampling becomes a problem. And you can never really be sure that you got close enough to the point. Sampling doesn't work. What else can we do? Okay, teachers can answer. Linearize. Right. So the phrase linearize it is such a tricky phrase in differential equations. You may ask yourself, what does that mean? And this is why in every single talk that anybody ever uses the word linearization in, I raise my hand and I say, what do you mean by that? Which really annoyed Kayaba. And I said, what do you mean by relinearization? It's like, what do you mean? What do I mean?
It's my favorite response. What do I mean?
So, linearization assumes that all of the different directions of these vectors are determined, well, actually, it's not really an assumption. All of the directions of the vectors at these different points are determined by these systems of equations. And you can always do a Taylor expansion using calculus around any point you like. And because these are like polynomials in 2 variables, then that expansion will just do what it needs to do. And the higher order terms in that expansion vanish nearby that point much faster than linear terms. So what is linearization in differential equations? What we do is we replace our system of differential equations with an expansion, Taylor expansion, polynomials. Now, I'm not actually going to write that out, but what I am going to do is I'm going to say, all right, after we expand this out into polynomials, then I will be able to write this system as follows. I'm using vector notation suddenly. I shouldn't use A, well, we'll use A0 and X0 until it's a problem. So what we do is first we find our equilibria, A0, X0, that's this point here. X0, A0. I did that backwards. which means I probably should flip this, whatever. And we, instead of looking at the whole system of differential equations, which generally is nonlinear, right? We have nonlinear terms here, and in a few minutes, we're going to have a lot more nonlinear terms. You just keep the value of the system at that point that you're interested in, and then you just keep the linear terms of the expansion and throw everything else out. Because everything else vanishes fast enough that this is going to be approximately equal to the degree of our satisfaction. And then what can we do to determine if this is spiraling in or spiraling out or not spiraling at all? Just looping. What can we do? I see some people who are acting like something just glimmered through their consciousness from when they took DVQ, but they couldn't remember it if they tried. What are you gonna say?
Like my instinct is it should be the determinant.
Yes,
Thing to do with the determinant.
absolutely. We look at the determinant of this matrix. And actually, to be more precise, we look at the eigenvalues and eigenvectors of this matrix. And we check whether or not the real value of those eigenvalues are negative. Because if they're negative, then in one eigendirection, everything is being sucked in, and the other eigendirection, everything is being sucked in. Okay. So if this matrix is J, this is going to be the last time I draw a matrix on the board, because in a minute it's going to be a big 5 by 5 matrix, and there's no chance that we're going to do a 5 by 5 matrix of polynomials and get the eigenvalues by hand in this today. Sorry, Jim. That's this weekend. Just kidding. So what we do is we look at the eigenvalues of J at these at this equilibrium, and we determine if the real parts are negative. So if the real part, I already used lambda, didn't I? We're going to change this lambda to mu because mu is more. Just hope for the best. If the real part of this matrix, of the eigenvalues of this matrix, I should do eigen. I'm not ruining this thing. Then this equilibrium is stable. And as it turns out, that basically, because of the way that this is structured, this is always going to be stable. Okay. So in terms of predator-prey equation, we never really need to worry about it. By the way,
This kind of problem, you're gonna get actually non-real complex with negative.
yes, sometimes you might get complex eigenvalues. That becomes the
That's
second half of the
that's
song. And today, I guess I'm just like doing a really good job of like leading people to my conclusions before I get to them. So I guess that means I'm a good communicator. That's all I'm saying. Okay. Now here's the problem, is that we have these parameters alpha and beta and now mu. And the eigenvalues of this matrix depend on those values. So the eigenvalues are actually functions of the parameters. Now here's the interesting thing. How many parameters do we have? What's a parameter and what's a population? Good question. Let's start with this. What's a parameter and what's a population here? I would call capital A population of ammonia molecules, and X a population of bacteria, right? Everything else is a parameter. So we have these parameters alpha, beta, and mu. That's a 3-dimensional parameter space for a 2-dimensional problem. The dimension of the parameter space is called the codimension of the differential equation. And we're going to get back to that. But here's what's interesting. And this is actually the real point of this talk, is to talk to you guys a little bit about bifurcation theory. What we're talking about fish tanks is like the nice shiny front wrapper, the bifurcation theory. If we imagine this matrix J for a high dimensional nonlinear system of equations, then all of the eigenvalues are going to be functions of the parameters, and the parameters are in a high dimensional space. And so sometimes what will happen is if you plot two eigenvalues, okay, question number one, why would I plot two eigenvalues in a two-dimensional equation? How many eigenvalues does this matrix have in general, even if they overlap? Two. So let's look at two eigenvalues, because in a two-dimensional system, not only do we have two eigenvalues, they're complex conjugates of each other. So if you compute an eigenvalue, then the other eigenvalue is just down here. And these are functions of these parameters, alpha, beta, and mu. So if you can imagine, I have a volume knob for the alpha parameter. And as I change it, these things wiggle around. But we know that they have to be stuck on a vertical line with respect to each other. Not sure if my hands are doing what I want. Now, pretty good. What happens sometimes is that if we start over here and we change a parameter a little bit, we end up over here. And that's really important because of this. If the real parts are negative, then the point is stable. If it's positive, the point is unstable. So as I change this alpha parameter, let's just draw it from over here. We start here, and these things may end up crossing the complex axis. When that happens, the sign changes. Suddenly, instead of having a nice spiral that moves inward, at the point where the eigenvalues are on that axis, it connects and makes a loop. And then a moment later, it's an outgoing spiral. This is catastrophically problematic. Can you see why? Not just for fish tanks, but like you build a machine, you model it with differential equations, this happens. What just happened?
Small change in the system induced large change in behavior.
Right. Small quantitative change in the system induced not only a large change in behavior, but a qualitative change in behavior. And if, let's say, this is the region of parameter space that your machine doesn't blow up, what happens if that happens? Your machine blows up. So sometimes these are called supercritical bifurcations. If it goes the other direction, it's called subcritical. You can think of that in terms of like nuclear bombs or whatever. Man, I'm gonna get on lists. Today we mentioned TNT and supercriticality.
So like hypothetically, you want it to like model nuclear criticality.
Oh, we're so far away from that. In this talk.
Okay, they fired the people to make those lists.
Right. Oh, yeah, that's. This is being recorded, Matt. Now, there are a bunch of different ways that eigenvalues can cross the complex axis. This is one way. It goes, there's another way where they crash into each other and then merge into a single and then move over. So, oh, there's another one. What happens if it moves over and just kisses the axis and then moves back? So how do you determine all of it? What is happening exactly? Well, actually, almost everything boils down to taking the determinants of these high dimensional matrices and running. Oh, dude, guys, my master's degree was on modeling neurons, and I had a two-dimensional system of equations with 4 parameters. And this thing was the biggest nightmare to compute the conditions under which it crosses the axis cleanly versus it crashes into itself. Like 5 pages of calculations. It all has to do with referring to weird quadratic form stuff that I never actually really understood. Never should have got my master's. Never should have got my master's. And I blame you. Okay, so this is the end game of differential equations analysis. If you can come up with a system of equations and then develop a complete portrait of how all of these things occur and exactly the conditions under which those occur, it's called a bifurcation portrait. And it is essentially the complete classification of a certain system of differential equations. And then differential equations is done. Like, done. There are open questions. I shouldn't exaggerate. But if you can manage to produce a bifurcation portrait, you are so much farther along the curve than that. Like, the only thing left is to start looking at functions that carry one differential equation system to another differential equation system. Different animal. So stability in differential equations and these qualitative topological changes that you detect with complex algebraic conditions. I think it's pretty cool. So let's keep working on our tank model and see where it goes. We're not going to do any more actual math. We're just going to be building, well, actually, I shouldn't say that. We are going to build a model, and we're going to do our best to construct extremely limited snapshots of part of the bifurcation portrait implied by the model. I think somebody posted an archive paper last year describing this system of differential equations or something similar to it, specifically for large scale aquariums. So like you go to like Sydney, Australia or something, they have an amazing aquarium. Never been, really want to go. But if you want to model that whole system, it's absolutely plausible. Of course, the higher dimensionality you go, the more likely you are to get a chaotic system that isn't really modelable, but that's a separate. So what we have so far, ammonia comes into the tank at a fixed rate out. It's eaten by nitrosamona at a collision rate of beta. And we have a death rate. Now, going back to the original model, the next thing in the system of equations was nitrites, okay? Which was the next species, chemical species, which I started with A. So we'll do DB dt. Now, every single time a nitrosamonobacteria eats an ammonia molecule here, it produces a new bacteria. But it also poops out a new nitrite bacteria. Has to happen at the same rate, at least in our model, because you could pick different parameters here and here and here. You know, you can make it as general as you like. It's just going to get nastier and nastier. So after we have nitrites being produced when nitrosamona reproduce, this should immediately raise alarm bells again. Anybody want to say why? Or guess why? It's the same problem as earlier. This thing isn't growing in a bounded way, right? Or it's growing in an unbounded way, I should say. So this problematically, if you don't add anything else to the equation, we have the ammonia being eaten by nitrosamona, which poops out the nitrites, and this grows unboundedly. So you just have more and more and more nitrates being produced in the system. And that's toxic. So eventually stuff's going to die. The next step down the chain, though, just like this is a chemical species and we use a function of this form, we're going to do the same thing, but down here and with a new parameter, with the next species in the chain, which was Nitrobacter. And now we have ammonia, nitrous ammonia, nitrites, Nitrobacter. I'm gonna write this down because I keep saying it over and over again. By the way, just like there's multiple forms of ammonia, there's multiple forms of nitrites. I'm just gathering them all together into a single variable. How many of you guys know a carnivore? Like one of those people who eats nothing but meat? It's gonna sound random. It's related, I promise. These people are crazy because they're like, people have been complaining about nitrites being toxic for years, but plants have more nitrites in them than meat. And those people have gotten nitrites and nitrates confused. And not only that, nitrites are not nearly as toxic to humans as they are to like a little tiny fish. I can have quite a few nitrites in my food without ever having a single negative impact. So if you ever meet a carnivore who's like all about nitrates and that's their like explanation for why they never eat spinach, just walk away from that person. Don't even try to like argue with them or anything.
There are plenty of other reasons.
Okay, now Nitrobacter, we're supposed to turn nitrites into nitrates, which are plant food. So they're also similarly, these need a death term. Give me a Greek letter.
New.
Ooh.
You pick new.
Yeah.
Nice. Wait, that's Ada. Which one's new?
It's like a.
Looks like a V.
Looks like a V, talks like a V. Okay, let's see. That's awful. That's an awful view. Okay, now at the end, we have the nitrates, which was chemical species. Oh, whoops. Now, again, this is a waste product from the Nitrobacter eating the nitrites. So it's going to increase at the same rate as the Nitrobacter. Nitrates were plant food. So those are going to be eaten by plants. And it's going to be exactly the same predator-prey equation. So it can be another Greek letter.
No.
How about capital C? I don't hate you guys that much. We'll do C, lowercase.
It's called a tornado.
Tornado. And so the nitrates are being eaten by plants.
Quite a tornado. That's all.
What else do plants need? Light. What do we not, like, we're completely neglecting the light cycle, which is this like forcing function, which turns the system of differential equations from a homogeneous system of differential equations to a forced differential or inhomogeneous system. We're not doing that today because bifurcation theory for inhomogeneous systems is literally sci-fi BS. I have read papers that are like, all right, take a trajectory and then take all points which have a trajectory passing through them, which eventually converge to that first one, and then take the limit of those initial conditions back. And that's like how they look at the stability of trajectories in inhomogeneous dynamical systems.
It's also all me.
We're not doing that today. Although I would love to do that. I think I am not at that point in my career. Now, plants have a limited lifespan. They also have a death term. Give me a letter for death for plants.
Delta.
Already used gamma. Huh?
Delta for death.
Delta. Yeah. Okay. So one question we might have is like, how could we modify this to take light into account? Well, when light is high, the growth rate should be high. When the light is low, the growth rate should be low. So we could just put like a function over time that goes from 0 to 1 and then 0 to 1 in like a square wave and put it here. And that turns on the growth and then turns off the growth. Turns on the growth and turns off the growth. And I'm using a square just because it's a square wave, not because I'm trying to like be like, all right, let's do the QED stuff. Because we're not done. Also, I don't think I have a concrete statement that I'm proving, so to say that I've finished and proven that which needs to be proven is not correct. Okay. Lastly, we have animals. We already used A. Let's do Q. P and Q.
F for fish.
Fish. Love it. Now, how do fish work? Well, if you only have one species of fish, super boring. Maybe interesting for the fish. The remaining part of this would involve splitting the fish population. Actually, we should also do this with the plant population, where we split the plant population into multiple plant populations, and each of them have different parameters, which are optimized according to the species. And then you split this up into different species of fish, or shrimp, or snails, or whatever you want. And then you build up all the different predator-prey relationships in the same way that you build predator-prey relationships between the chemical species and the bacterial species. Except, what good is 2.5 fish?
A lot.
You'd eat it.
Live
Very
fish. What good is counting countable objects with the real numbers? But let's put it another way.
We're not measuring fish based on weight.
So actually, the first time I did this model, I did everything by biomass instead, and actually it's super, super easy. But this is more interesting, in my opinion. What you can do is instead count the animals, but then we have this nice, smooth, continuous system of differential equations. And then here we have to start counting things discretely. Concentration of fish. Fish per fish. If you like fish inside your fish.
I like that.
Fish per square meter.
Fish per light year. So the issue is now, these are supposed to be discrete population. How in the world do you handle blending a continuous thing with a discrete thing? Good answer. That's a really good answer. How many of you guys know what a Poincare section is? I probably pronounced that Poincare. I don't think it's probably incorrect also, and now it's also recorded. So now I'm on record forever speaking one of the most famous names in differential equations incorrectly. How many of you guys know what a Poincare section is?
Maybe spell that.
Poincare, but the I is decorated somehow with a with like a, yeah, I'm not sure what's a. So I didn't lose your chalk, did I?
Yes.
So the way a Poincare section works, and I'm gonna just pretend that I spelled that correctly. Imagine you have a very high dimensional space. Wrong location.